Welcome to session 9 of UGBS 301. In our previous sessions, we looked at interval estimation for a single population and also for proportion. In this session, we would continue with confidence interval estimation with a focus on finding the confidence interval for the differences between two proportions. Therefore, after completing this session, you should be able to compute confidence intervals for populations for the difference in means for two independent means where the standard deviations are known, and also in situations where the standard deviations are unknown. We would also be able to compute confidence intervals for the difference in means for two means from paired samples, and also the difference between two population proportions. We are going to start with population means for independent samples. So, our goal, or our major goal, is to form a confidence interval for the difference between two population means, that is mu1 minus mu2. And these groups are independent in such that the elements that are presented in group 1, or the elements that are present in group 1, are not the elements that are in group 2. So the elements in group 1 are different from the elements in group 2. Therefore, the point estimate for the difference is also x bar 1 minus x bar 2. Independent sample, as already explained, means that they are unrelated. The sample selected from one population has no effect on the sample selected from the other population, and we are just looking at the difference between two sample means. We would consider the situation where the two population standard deviations are unknown, that is sigma 1 and then sigma 2. Our assumption is that samples are randomly and independently drawn, and population distributions are normal, or both sample sizes are greater than or equal to 30. We also consider that our population standard deviations are also known. Given that our population standard deviations are known and both populations are normal, or both sample sizes are at least 30, then our test statistic will be given as, or our standard error will be given as sigma x1 bar minus x2 bar is the square root of sigma squared over n1, that is for the first group, plus sigma 2 squared over n2. Now note that the addition of these values is all under the square root sign. Therefore, a confidence interval for the difference between mu1 and mu2 is given as x1 bar minus x2 bar plus z alpha over 2, then the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. We take an example. The Ghana Clinic Company operates 20 medical clinics in Ghana, and as part of the company's ongoing efforts to examine its customer service, GCC observed 100 male and 100 female patients at the clinics to estimate the difference in mean time spent per visit for men and women patients. The sample means were 34.5 minutes for males and 42.4 minutes for females. Previous studies indicate that the standard deviation is 11 minutes for males and then 16 minutes for females. Help GCC to develop a 95% confidence interval estimate for the difference in the mean times. So, our measure of interest, as stated in the question, is to find a confidence interval estimate for the difference in means, which is actually mu1 minus mu2. And hence, our point estimate is given as x1 bar minus x2 bar, which is 34.5 for the males, that is group 1, and then 42.4 for the females, which is group 2. And that gives us a difference of negative 7.9 minutes. That is, women in the sample on the average spend 7.9 minutes longer at the clinics than their male counterparts. A standard error is given at the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, which gives us 11 squared divided by 100 for that of the males, because we said their standard deviation was 11 minutes, and then 16 squared over 100 for the females, because we said their standard deviation was 16 minutes. Note that the sample size for both males and females were 100 each. This gives us a standard error of 1.9416. Note that we are constructing a 95% confidence interval, and therefore our Z alpha over 2 is equal to 1.96. So our confidence interval, or our 95% confidence interval for the difference, is giving us x1 bar minus x2 bar, which is actually negative 7.9, plus or minus 1.96 times the standard error, which gives us negative 7.9 plus or minus 3.8056, giving us a lower bound of negative 11.7056 and an upper bound of negative 4.0944. That is, based on the sample data, a 95% confidence and a 95% confidence level, women spend on the average between 4.09 and then 11.71 minutes longer at the clinics than their male counterparts. We are going to look at situations where we have sigma 1 and then sigma 2 being unknown, but our sample sizes are large. So in these cases, in the initial case, we looked at when the population standard deviations were known. This time we want to look at when the population standard deviations are unknown. The assumptions are these: samples are drawn randomly and independently. Both samples are large, that is greater than 30, and then the population standard deviations are unknown. In determining that, we therefore use the sample standard deviation to determine or to estimate the value of the population standard deviation. And our test statistic is a z-value, and it's a z-value because of our large sample sizes arising from the central limit theorem. Thus, our confidence interval estimate will be given as x1 bar minus x2 bar plus z alpha over 2, then s1 squared over n1 plus s2 squared over n2, all under the square root sign. The only thing that has changed in here is that we've used the sample standard deviation to replace the population standard deviation in the previous case. When you are looking at situations where sigma 1 and sigma 2 are unknown, that is, our population standard deviations are unknown, and our sample sizes are also not large, that is, they are small, we also assume that our populations are normally distributed, our populations have equal variances even though they are unknown, and then our samples are independent. Given that, in forming the estimate, we also assume that our population variances are assumed equal, as we've already said, and the test statistic is a t distribution that has n1 plus n2 minus 2 degrees of freedom. We realize that because we've assumed that our population variances are equal, although unknown, we therefore estimate what we call a pooled standard deviation. A pooled standard deviation. And mathematically, the pooled standard deviation is defined as the square root of the first sample size minus 1 multiplying its sample variance, that is s1 squared, plus the second sample size minus 1 multiplying its sample variance, all divided by N1 plus N2 minus 2. You will see that this N1 minus N2 minus 2 will translate to be the degrees of freedom for our T distribution. Therefore, our confidence interval for mu1 minus mu2, given that our population standard deviations are unknown and our sample sizes are small, it's given as x1 bar minus x2 bar plus or minus T alpha over 2 with N1 plus N2 minus 2 degrees of freedom, multiplying our pooled standard deviation, or our pooled standard deviation times the square root of 1 over N1 plus 1 over N2. And this here is the definition for the pooled standard deviation as we saw in the previous slide. Let's take an example. A recent study was conducted to estimate the difference in mean annual contributions for individuals covered by two pension plans, SNP 1 and SNP 2, during the past year. A simple random sample of 15 people were selected from the population who have SNP plans with the following sample results. In the first sample, we have N1, that is the first sample size, was 15. Then their first sample mean, as in for SNP 1 group, the sample mean was 2,119.7, and their sample standard deviation was 709. Similarly, for the second group, they had a size of 15, a sample mean of 1,777.7, and a sample standard deviation of 593.9. Assuming that we have a confidence level of 95%, we would like to consider or construct a confidence interval for this difference in average contributions. So mu1 is the mean contribution for investments in SNP 1, and then mu2 is the average contribution for investments in SNP 2. Therefore, since we see that our sample sizes are small, as in they are less than 30 for both situations, and also our population standard deviations are unknown, which have been estimated using the sample standard deviation, we are going to use this relation to calculate our confidence interval. So our solution will be such that, first of all, we try and find the pooled standard deviation. And it's giving us 15 minus 1, that is the first sample size, plus its sample variance, that is 709.7 squared, then plus the second group 15 minus 1, multiplying its variance, which is 593.9 squared, all dividing 15 plus 15 minus 2. And this will give us a value of 654.37. Similarly, the difference in terms of the means will be 2119.70 minus 177.70, which will give us 342. Then we have our T statistic, which is actually a T distribution, which is alpha over 2, which is 0.05, and then a degree of freedom of 28, giving us a T value of 2.04. When you put all this together into the relation, we have a lower bound of 147 cedis.45, and then an upper bound of 831.45 cedis. Therefore, we believe that the 95% confidence interval for the estimates for the difference in the mean contribution for those who contribute to SNP 1 versus those who contribute to SNP 2 is 147.45 cedis, lying between 147.45 cedis and then 831.45 cedis. Let's take another example. The head of research and development at NS Chemist is interested in estimating the difference between individuals aged 50 and under and those over age 50 years old with respect to the mean time from when a patient takes a new medication until the medication can be detected in the blood. The company would want to use this information to guide doctors in how to advise their patients to use this new medication. So for those who are aged 50 years or younger, we took a sample of size 6. And those who are aged over 50 years, we took a sample of size 8. For the first group, we had a sample mean of 13.6 minutes with a standard deviation of 3.1 minutes. For the second group, we had a sample mean of 11.2 minutes with a sample standard deviation of 5.0 minutes. Of course, our mu1 and our mu2 are the mean time spent by people who are aged 50 years old or younger, and those who are aged 50 years, over 50 years, respectively. Therefore, given that our sample sizes are small, and then our population standard deviations are unknown, we are going to calculate the pooled standard deviation on the assumption that the unknown population standard deviations are equal. And hence we get n1 minus s1 squared, which is giving us 6 minus 1 minus 3.1 squared, plus n2 minus 1 times s2 squared, which is giving us 8 minus 1 times 5.0 squared, divided by n1 plus n2 minus 2, which is 6 plus 8 minus 2. That gives us 4.31. Therefore, a 95% confidence, at a 95% confidence level, we have that the confidence interval will be given as the difference between the means 13.6 minus 11.2 plus or minus the value of our critical our t distribution multiplying the pooled standard deviation times the square root of the sum of the sample sizes. That gives us a lower bound of 2.4 minutes and an upper bound of 5.0715 minutes. That is to say that the 95% confidence interval estimate for the differences in mean time spent taken for medicine to be detected in the blood sample or in the blood between the age group of 50 years or younger and over 50 years is giving us negative 2.67 minutes and then 7.4715 minutes. From the calculations, we realize that we have a pooled standard deviation of 4.31 and then a t value of 2.1788 as in t alpha over 2 with 12 degrees of freedom. Therefore, calculating our confidence interval will give us 2.4, that's the difference between the means, plus or minus 5.0715. So we are going to have a lower bound of 2.4 minus 5.0715, which gives us negative 2.6715, and an upper bound of 2.4 plus 5.0715, which gives us 7.4715. And this tells us that the 95% confidence interval estimate for the difference in the mean time spent taken for the medicine to be detected in the blood between the first group and then the second group is giving us a lower bound of negative, is lying between negative 2.6715 and then positive 7.4715. Now, since this interval lies between a negative number and then a positive number, it means that it includes 0. Therefore, the researcher cannot conclude that a difference exists between the age groups with respect to the mean time needed for the medications to be detected in the blood. That is, it does not seem to matter whether the patient is 50 years or younger, over 50 years. This also means that practically no advice for the doctors is warranted. we look at the paired samples. In the previous situations, we considered independent samples, and we said that these groups were unrelated. In paired samples, we are saying that these groups are related, or they are matched, or they are repeated measures. This could be a before or after treatment. In a paired samples, it means that the individuals within the first group are the same individuals within the second group. In analyzing paired samples, we use the difference between the paired values, which is D equals to x1 minus x2. And our assumptions are that both populations should be normally distributed, or if not normal, we are going to use large samples. So, our difference, or our ith difference, or the difference in the individual groups will be x1i minus x2i, which means that the difference in one individual in group 1 minus the difference in that individual in group 2. We estimate the mean for the differences, which is the summation of all the individual differences divided by the square root of n. And we also calculate the standard deviation of the differences, that is the di's. In constructing the confidence interval for d bar, we are saying that d bar, or the confidence interval, is given as d bar plus or minus t alpha over 2 times the standard deviation of the differences over the square root of n. T alpha over 2 has n minus 1 degrees of freedom, and n is the number of pairs in the paired sample. We take an example. The IT manager of the Ghana Ports and Harbours Authority is trying to convince the Chief Executive Officer that recently released cargo tracking and payment software by TechSafe Instruments is faster than that of the existing one by Orasoft. 5 workers were randomly selected to run both TechSafe and Orasoft softwares for cargo tracking and payment. The table below shows the time in minutes spent on both softwares. So since the 5 workers were randomly selected to use both TechSafe and then Orasoft, this is a paired sample. And you could also see that the sample size in TechSafe is the same as the size in Orasoft. To determine this, you first have to calculate the means, the differences. So we could do the time for TechSafe minus the time for Orasoft. So in calculating, we are going to have 58 minus 47, 52 minus 53, 64 minus 54, 68 minus 60, and then 57 minus 58. So we are going to have 58 minus 47, that gives us, say, 5. 52 minus 53, which gives us negative 1. 64 minus 54, that gives us 10. 68 minus 60, that gives us 8. And then 57 minus 58, that gives us negative 1. Based on these values of D that you get, you'll be able to find the average value of D, and you'll also be able to find the value of the standard deviation of the differences. Based on these things, you will be able to calculate your confidence interval, given that you have your t distribution, which is t alpha over 2, and based on this question, our sample size for the pairs is 5. Therefore, our degree of freedom will be 5 minus 1, which is 4. We would like you to try this question for yourself. This brings us to the end of session 9. Thank you very much.